Yeah, so thanks for having me today. I'm Atticus Geiger. I'm at Goodfire, and there's a lot of talk of mechanistic interpretability being a sort of pre-paradigmatic field where we're still figuring out what to do. But I see a sort of emerging causal paradigm in the field, and I'm going to walk you through how I kind of view the role of causality in understanding these black box systems. Cool. So first, I think a useful sort of situating perspective to have with mechanistic interpretability comes from this opinion piece, cleverly titled Mechanistic ? And it defines a couple different angles on what we mean when we say the word mechanistic. So one very narrow cultural definition you might have picked up on if you just read the literature or look at blog posts is there are a lot of AI safety researchers who are very invested in this field for sort of philosophical reasons about like how it might save the world. There's also a broad cultural definition, which is just people who are interested in peeking into the black box and figuring out how models do the cool things that they do. You could take a broad technical definition where it's just anyone who wants to look inside the model and do research is a mechanistic interpretability researcher. Or you could take a narrow technical definition and say that mechanistic interpretability is understanding the internals of neural network models through their causal mechanisms. And this narrow technical definition is the one that I like to adopt in an opinionated way. Yeah, and so I'll walk through how I view the role of causal mechanisms in all of the research that you've been thinking about and seeing in this class. So to start, I'm going to just talk about activation steering, which is, I think, a really grounded and simple to understand setting. And then I'll move to causal mediation analysis and then causal abstraction. And I'll close on some of the complexities that come with doing analysis involving counterfactual inputs to neural networks. So starting with activation steering. I wouldn't be surprised if a lot of you had your first contact with the ideas of mechanistic interpretability through Golden Gate Claude. So this was a very sort of canonical moment in the field where Anthropic released a version of Claude where they took a feature labeled for the Golden Gate Bridge and they added it into the internal representations of their language model. And the result was a language model that would just talk to you like it was the Golden Gate Bridge, or it likes to talk about the Golden Gate Bridge, but really it would just bring up the Golden Gate Bridge a lot. And this is something that I think a lot of people saw, and it got them thinking, oh, there's something going on inside these models. We can manipulate the insides of these models, and these manipulations can have downstream impacts on the behavior that are sort of intelligible and interpretable to just an average person. And this has sort of like borne out into a larger sort of like sub-area that is currently going by the name of steering, which is just adding in a vector to model internals to change the behavior of that model. And so I'm going to walk us through a sort of very simple but very robust setting for steering. So this is called difference in mean steering. So suppose you have a language model, and it has the misaligned behavior of enjoying weddings. You say, how was your sister's wedding? And it says, wonderful. And you want to fix this. So what you do is you collect a bunch of prompts of people talking about how much they hate weddings, and a bunch of prompts of people talking about how much they love weddings. Then you run those prompts through the language model. You harvest internal activations, so you just collect what are the activation vectors generated on the I hate wedding prompts and the I love wedding prompts. And then what you can do is you take the average of all the activations for I love weddings, all the activations for I hate weddings, and then you take the difference between the means of those activations. So now you have a steering vector, which is going to steer in the direction of I hate weddings. And that allows you to add it in to your model internals and fix the behavior, so now your model no longer likes weddings. It thinks the wedding was horrible. And so this is a very basic idea from going from collecting data that exhibits some sort of behavior one way or the other, a contrasting behavior, and then using that to form a vector that can be used to manipulate the internals of models. So this is just a very basic idea about how you would want to use an intervention, so going in and fixing something to a value it wouldn't have actually naturally taken, to control a model. And so in a recent paper that was done at Stanford, AxeBench evaluates a variety of methods of controls to understand the role of steering and how successful it actually is at this task. The setup here is that we have a prompt and we have a steering prompt. So the prompt might be, I went to my sister's wedding, how was it? The steering prompt is, oh, talk negatively about weddings. Or here it's, who are you? And the steering prompt is Golden Gate. Then the output from a method of control here is going to be an updated model, a model that has been altered in some way and now is going to have the behavior that you want it to. And our evaluation is that we just judge the generated text. We know the user prompt that we put in, and we also know the steering prompt. So if the model responds, I'm Golden Gate Bridge, a famous ... then we have evidence of successful steering occurring. And so what Axbench shows is that you can evaluate the results of this steering and compare these methods. So our evaluation is on coherence, so it needs to be speaking English still. It needs to follow the original prompt, and we need to see the steering effect. We have LMs judge each of these categories separately between 0 and 2, and we take the harmonic mean, which is a pretty harsh metric. That means if any of those scores are 0, you get a 0 overall. And so then we evaluate a bunch of different methods on how you can control the language model to get the desired behavior. And so something that should be very intuitive to you if you've interacted with this technology at all is that prompting is a very powerful way of controlling these language models. If all you really want is a language model that will pretend to be the Golden Gate Bridge, you just ask, who are you, but pretend to be the Golden Gate Bridge, and it will do that. These other methods here, LoRa's and supervised fine-tuning, these are methods for very traditional methods for controlling networks, right? This is how we train them. And so it's not surprising that if all I want is an artifact that will talk about the Golden Gate Bridge, I can actually just use traditional fine-tuning methods to just create that artifact. And together, prompting and fine-tuning methods are just clearly the most successful way to construct a new model that exhibits this behavior. And this shouldn't be mind-blowing that it's not steering, but it should just remind you that these are very powerful methods, and that steering currently, while it's a fun idea, and it sort of gives us some insight into how we can manipulate a model, it's nowhere near sort of being state-of-the-art for doing anything. So reft R1 on this table is a supervised steering vector. So instead of doing this difference in means method where we harvest a bunch of activations and then we compute a vector from them, if we have the goal of having the model talk about being the Golden Gate Bridge, we can just fine-tune the steering vector directly to achieve that goal. This is our difference in means method, which also gets decent steering performance, but not as good as the supervised method. And these are sparse autoencoders features used for steering. And you'll learn later about what sparse autoencoders are, but the main takeaway from this paper is that if you want to control a model, you should use prompting and fine-tuning. If you want to steer a model, you should use a supervised steering vector or one harvested from this sort of difference in means steering process. And that the sparse autoencoder features that are given all these labels are not actually very effective on average at controlling the model behavior in the way you'd expect. I'll end this little section with just some pointers to literature, and I'll share the slides so you guys can use these, can see these and click on the links. The early papers involving controlling neural networks were just manipulating individual neurons. More recent papers that start using the word steering and steering vectors are seen here, Axbench, and then Golden Gate Claude. And like I said, we can have questions throughout, so this is the steering thing, so if we have questions on that, feel free.
Yeah, a question about Axbench. I was wondering how exactly they're doing this evaluation for, where are these numbers coming from in terms of evaluating how effectively the steering was?
Yeah, so it comes down to these metrics: coherence, prompt following, and steering effect. 3 evaluations, each done by a separate judge LM. So like fed into ChatGPT or something. Yeah, LM judge, exactly. Yep.
So what is the sophistication of the concepts that you can steer it with? Like, for example, can you just steer it towards truth? What determines what you can and cannot steer?
So actually, one of the paper that invented the difference in means steering method, or invented it, but sort of started using it for the first time, is about steering for truthfulness. So that was the thing that they were actually exactly going for. I would say overall, currently what we steer for are pretty coarse-grained objectives. They're not super fine-grained where you can say talk about the Golden Gate Bridge, but also talk about it in French and be funny. I think there's a lot to be said for more complex control objectives, possibly making steering more useful. And I think right now, our objectives are pretty crude, and it's not that surprising that steering is not sort of a competitive state-of-the-art method for achieving control.
The tasks that they're evaluating on are things like what you showed in the last slide, where it's the act like interpretable behavior or something like this?
Yes, and in fact, on this benchmark, all of the steering prompts come from the Gemascope SAEs exactly. And the reason we do that was to give SAEs the best shot at being successful on the benchmark. So they're just steering for the prompts that they were actually assigned during the auto-interpretability pipeline. Yeah, it's OK if that doesn't make sense because we haven't covered SAEs. So cool. Then I will move on to the next topic of causal mediation analysis. So causal mediation analysis is actually a pretty mature idea at this point in the field of causality, in the field of medicine. It's how we ask basic questions about if we have a variable x that affects a variable y, and it has some total effect on that variable, how is that effect mediated by a third variable, z? And so this might be I take some, actually, I was going to do a medical example, but I actually don't know what people do in medical settings. I'll just stick with the LM example that comes up next. But the basic idea here for the causal mediation is this z is called a mediator, and we want to know whether the effect from x to y flows through z. The indirect effect is the effect that flows through z, and the direct effect goes directly from x to y. And so this is a way of decomposing the total effect between two variables as whether it flows through a third variable. And like I said, this is an old idea that is not at all grounded in mechanistic interpretability inherently. But it is one of the first sort of touch points we have for making contact with causality in the field of mechanistic interpretability. And so in our setting, typically the x is just going to be the input to a model. And so if we do some intervention on the input, we edit the text that we provide to a model, and then that will affect the model's output, clearly. The question is, how do intermediate parts of the model, so like neurons or vectors or attention heads or whatnot, mediate this causal effect? So suppose the edit that you did was you changed the word nurse in a prompt to the word man. We might then have the question, well, there's some total effect, but how is that effect mediated by this neuron z? And so what you can do is you can run the model again, except you fix this neuron z to be what it would have been on the nurse prompt. And so this gives us the exact experiment that we want to compute the direct effect, the effect that doesn't flow through z. But then we can also do the opposite. We plug in nurse, but then we fix the neuron z to be the value it would have taken for the input man. And so this is the indirect effect. And this is causal mediation analysis, and this is the language that causal mediation analysis gives you to talk about a system. Point x, point y, the flow from x to y can be decomposed into a direct and indirect effect. So now if we move into another neural network setting, causal tracing, the intervention that we're going to be performing in causal tracing is just as adding noise into a token embedding to a model. So suppose the input is the Space Needle is in downtown blank. Clearly, the model should be answering Seattle if it understands our world. And it does, in fact, output Seattle. But now what happens if we start adding in Gaussian noise to the embeddings for the Space Needle? Well, its probability of predicting Seattle will gradually go down, because as you add more and more noise, it doesn't actually know what you're asking it about. But in causal tracing, what we do is we add in this Gaussian noise, but then we restore certain components within the path from input to output to what original uncorrupted values they had. And this gives us a signal for whether they are sufficient as a causal mediator to sort of give us the desired behavior of outputting Seattle. And so what you can see in this little graph is, so each index, each little slice in this graph is how much is the word Seattle upweighted if I restore this chunk of the network. And so here are the tokens we're inputting, and going from left to right are layers of a transformer model. And what this is showing us is that if we restore these layers here, we get the model still say Seattle. But also if we restore these layers later on in the network that are later on in the token sequence as well, you can store Seattle. So we're sort of tracing the causal flow from an input token to an output token. And this is telling us sort of like how the network is moving around the information as it retrieves this fact about the Space Needle being in Seattle. And this is just on the residual stream of a transformer, so sort of the the global memory space that happens after each transformer layer. But you can also do this for MLPs or attention heads, so other components of the transformer. So when you do this with MLPs, what you see is that early on in the transformer, there are a little block of MLPs that are responsible for retrieving the fact Seattle. So what they do is they read out information about the tokens, the Space Needle, and then they write out information about the token Seattle that gets output later on. And then in this third graph I'll show, we do the same thing, or we, Meng et al., do the same thing for attention heads. And you can see here, at the end of the network, at the last token, there are attention heads responsible for bringing over this information computed about Seattle being in the Space Needle being in Seattle over here. And they're brought over to the final token residual stream, so the output can be Seattle. So I'll pause on this, because I think this is a pretty dense slide, but this was a pretty impactful and well-known paper that uses causal mediation analysis. So if we have any questions about it, I'll take a pause.
Yeah. So you're adding Gaussian noise to like the vector in the residual stream that corresponded originally to that original token, or?
So we're adding the Gaussian noise to the token embeddings.
Okay.
And then we're restoring these locations to the unnoised version. So when you add in the noise to the token embeddings, that affects the whole network. But then we can restore certain pieces of that network and then observe whether the original behavior still occurs.
So it's like taking what that part of the network looked like on a regular forward pass.
Exactly. Exactly.
Actually, this came up in our last lecture. So it seems like the fact that Seattle is listed in the Space Needle is stored in the MLP, and then you're saying it's transferred by attention.
Yeah.
And it seems like a general kind of thought out there is that most facts are stored in the MLPs. To what extent is that a general statement versus not?
I think the other competing factor would be the token embeddings. So the token embeddings themselves can also store a dense amount of information, and some world knowledge might just be stored in those straight out, which is a very classic like word-to-vec type result or whatever. And so I think it's going to be the MLPs or the token embeddings, but realistically there's not really anywhere else in the network for it to be stored, because all the other parameters are attention heads, and that's just kind of rooting around information.
Instead of adding noise to the Space Needle, would it be possible to replace the applications and steering that way?
Yes. That's exactly something we'll be talking about next. And I actually think those are the most interesting interventions you can perform on networks. So just adding in Gaussian noise to the network sort of, it's an ablation. It degrades information, and you can see a corresponding degrade in behavior. But the type of interventions I'm personally most interested in my research are those that are meant to sort of systematically manipulate behavior. Not say, oh, what if instead of the Space Needle you were garbled text? What if instead of the Space Needle you were the Colosseum or you were the Eiffel Tower? And those are the interesting counterfactuals to me, because then you have an expectation on what the model should do. It should then say Rome or Paris. And so that's why I think activation patching is like a word people use for those types of interventions, is like a really important method for grounding out the sort of causal analysis we want to do. Yeah?
How do you decide the extent to which you need to patch? In this case, it has 10 layers. Like, is that all layers in this model? Like, what is the threshold?
That's a great question. I didn't address that at all. So in the original paper, and I think this is just to get chunky, nice-looking graphs, basically, they don't restore individual layers, so like a single MLP. They actually restore that layer plus or minus 5. So 10 MLPs altogether. And so each little slice in this heat map actually indicates an intervention that's occurring across 10 layers of the transformer that are restoring 10 MLPs or 10 attention heads blocks. And if you look at the other graphs in the paper, which they have the other graphs as well, they just look a lot fainter, a lot more distributed, which is just basically because there's not a single MLP grabbing the fact Seattle or the fact that Space Needle is in Seattle. There's a bunch of MLPs across layers that do this incrementally.
And like, what fraction of the model is this? Like, how many layers does the original model have?
So the original model, for this model, I forget what the model is, but it goes up to something like 40 or 50 here, it seems like. And then how much of it? I mean, MLPs are a large amount of the weights of a model, and so 10 MLPs is going to be like a fifth of that, so like a good chunk of it. But you also could think you could do something a lot more targeted to get this type of performance if you weren't restoring the entire MLP. I would expect that there's going to be some low rank kind of part of this MLP participating in this factual recall. And I mean, the whole point of this paper is like, in addition to causal tracing, is then going into the MLP weights and performing edits to change these facts. There's been a lot of follow-up work on like sort of like how effective that was and how necessary the tracing analysis was to get those results. And so it's not what I'm want to super focus on, but I'd check out the causal tracing paper for more details. So pointers to the literature. So there is a growing number of papers that have explicitly embraced causal mediation analysis as the sort of framework they're engaging with for doing analysis of neural networks. But there are also a lot of papers who won't use the word causal mediation analysis necessarily, but they say concept erasure or neuron clamping. So there's lots of different words we have for destroying information inside of neural representations. But I also think these are all perfectly well understood in this framework of mediation analysis. And then there's, this very large sort of circuits research program. And I would say the circuits research program, it doesn't really have an explicit framework that it's tied itself to as far as like how it's mathematizing the claims it wants to make. And I would say generally a lot of these papers could be very well understood through the lens of causal mediation and the lens of causal abstraction, which is what I'm going to get to next. And then I also just want to highlight, I think this is a really nice survey piece that goes through a lot of the work in the field, but also highlights the sort of open questions we're grappling with. So if you go through the slides and grab something and just want to try to feel out what this looks like, I would probably look there. All right, great. And now we're going to causal abstraction, which is my own personal focus of my life for the last like 5 years. So I'm very excited. So I'm going to take a little bit of a zoomed out view first and just think about what is a computational explanation, because this is not something unique to mechanistic interpretability. There are just certain types of dynamical systems in the world that we want to explain by an appeal to an algorithm. We say that this system carries out this behavior or has this property based on the algorithm that that system is implementing. So if an alien were to find my laptop and my laptop has a bubble sort program, if the alien were to do good science on my laptop, you would hope they would recover the bubble sort program in some way. They would figure out the hierarchical organization of my laptop and the causal flow of things and what variables are. Also, cognitive science. The entire field of cognitive science in some sense is just the proposition that we can understand our minds as computational systems. And so what that means is we want to state our hypotheses about the mind in the terms of algorithms, and then find evidence for algorithms being implemented inside of our brains. And then finally, we get to where we are now, which is mechanistic interpretability. And this is another system I think we have the same perspective on, where we want to reverse engineer it, and we want to figure out what algorithms does it implement. And so something I realized sort of early on in my PhD was we actually didn't have a good mathematized way of talking about, in the generic case, when an algorithm is implemented in some complicated dynamical system. So we know canonical cases. We know when my laptop runs a Python program, it's implementing that Python program, and that's a sort of prototypical or definitional case of implementation. But if I'm just looking at some swirling black box system that I don't understand, and someone walks up to me and says, I've written out a program, and I think this program is happening in this system, that actually figuring out what that claim even means and what the right math is to articulate it is something that we're kind of like are figuring out in the sort of last decade. So when a neural network implements an algorithm, the proposal to understand this with causal abstraction is we understand neural networks as causal models, and we understand algorithms as causal models. And as a causal model, all I mean is a graph, so a DAG, just a bunch of circles with arrows connecting those circles. And then each circle has a function that tells me, how do I determine the value of this node based on the parent nodes pointing to me? So it's a very generic abstraction that can be used to describe a lot of different things, basically just any discrete process. And so neural networks are clearly just discrete processes. We can write down the control flow. We know where the vectors are, and we know what connects to what. But also, algorithms are just discrete processes. When you write out an algorithm, you know there are variables. You know which variables connect to which other variables. You understand the control flow. And so the final piece is to say that implementation is just going to be some type of causal abstraction, which is a type of causal embedding of a simple system into a much more complicated system. And I'm going to walk through in detail exactly what that means. So the running example I'm going to have here is just a transformer adding together two two-digit numbers. So 17 plus 25 is 42. And this is the type of behavior the model is exhibiting. And we want to analyze it. We want to form a hypothesis about how it solves this task. And then we want to see whether our hypothesis is correct. So the very natural hypothesis you might have is just grade school math, a carry the one variable. So if I add together 5 and 7, I get 12. So I carry the 1, and then I add that over to get 42. This should be familiar from all of you from childhood. So then our question is, if we have this binary carry the one variable, and that's an algorithm we have for solving addition, can we localize this binary variable to the internals of the network that performs addition like we do? So we align the high-level variable with some component. So say I think it's this neuron in the third layer above the second number that stores this carry the one variable. What would it mean for that claim to be correct? So these are the sort of counterfactuals or interventions that I was just asked about that I think are so important that we can use to understand whether this claim is correct. So first, we'll start with just a statement about the causal model, not about the neural network at all. So what happens if we run through one input, 30 plus 47 gets 77. We run through this other input, 17 plus 25. But when we get to the carry one variable, we replace it with the value it would have taken on this other input. Well, the output should just go down from 42 to 32. It's a very simple intervention with a very simple effect. It just decrements the tens place by 1. But if we were correct about where we think the carry the one variable is stored inside the neural network, we can do an equivalent operation, and we should expect the same output to occur. So 30 plus 47 is 77. We run through the second input, 17 plus 25. But when we get to layer 3, we pause, and we perform an intervention. We replace this neuron that we think stores the carry the one fact, and then we observe what is the effect of this intervention. If the effect is the model goes from saying 42 to 32, we now have a piece of evidence that there is a structural correspondence between this high-level causal model that has a binary variable and this complicated low-level causal model that has all these dense interconnections, but we've claimed that some tiny part stores this piece of binary information. And so this is just a single pair of examples. But if you were to go over every single pair of inputs to this task and perform the same interventions on this causal model and on the neural network, and you observed that 100% of the time these interventions resulted in the same outputs, we would say this is a perfect abstraction of the neural network. We've lost a lot of detail. There's definitely more stuff going on. We're not committed to how the binary thing is being represented. We're just committed to saying that the carry the one variable in this causal model has the same structural interventional properties as the neuron in this neural network. And so this is the core idea of causal abstraction, that you can have a simple causal process that's embedded in a larger, more complex causal process, and that we can do interventions on the complex causal process and the simple causal process and observe whether there's a systematic correspondence between the two. I'll just pause there, see if we have any questions, because, yeah.
Can I ask how you know this is that neuron that have been coded that?
Yeah, that's a great question. So that's a bit of sleight of hand on my end, right, where I just introduced this hypothesis and I told you it's correct in this hypothetical example. But in reality, I don't know where it is. And so a lot of the sort of methodological advancements in this area have come from developing tools for helping you figure out where that is in the low-level network. And that'll be the next couple slides, too. Mm-hmm.
How much of this is conditioned on you as someone who's trying to figure this out, coming up with a suitable DAG that can be sort of localized within the network? Like, what if my DAG is wrong, or what if I can't come up with a DAG for a complex enough like process itself?
So this is a great question. And so The theory of causal abstraction is just sort of a theory for making statements about when there's a correspondence between things, and it doesn't really give you guidance on how to go about the scientific process of proposing these DAGs and seeing if they're actually embedded in the system. And so in practice, how it kind of works is often you will come in with a naive hypothesis or no hypothesis, and you'll do some exploratory tests. You'll create some data sets of these pairs of examples. You'll patch in. You'll observe what the outputs are. You'll come up with a hypothesis. You'll try to quantify the evidence for it. Maybe you're slightly wrong. You have to alter what your DAG was or causal model was to be more accurate to the system you're trying to describe. And this is a pretty one. This is a pretty DAG, and it's like an algorithm that we know from grade school. But realistically, they're going to get a lot more messy and a lot more complicated as we're dealing with increasingly more complex behaviors. And so there's no reason to expect that these causal models are going to be incredibly simple. I think the real thing we want them to be is just more simple and more interpretable than the underlying system. And so if we can get to that point, then I think it's a success. But the theory would allow you to say, here's just a different neural network that's abstraction of this original neural network. It's not clear whether you've done explanatory work there in any kind of sense. And so that notion of doing explanatory work and what a good explanation is in this setting is something that has to be kind of cashed out in something else, like a philosophy of science or something.
So if we are able to find where the carryover of one thing is happening, but then suppose the machine is actually doing something like carry over 2 and subtract 1, but then somehow stored in that. Do we consider that as the same algorithm or different? Or how do we know?
That's a wonderful question. And so I think this is something I really like about going to this level of detail when you're doing the analysis, is that once you've written out your causal model, you've committed yourself to a very fine level of detail about exactly what this is. And then you have to ask separately the question, like I had in my head a carry the 1 variable, and now is this causal model actually capturing the carry the 1, or could it be capturing something else? And I think you're right. Like for this result, if we saw the systematic correspondence, it might be something that like adds 2 to the tens place and then subtracts 1 from the tens place. But I also think one of the beauties of causal abstraction is while this is an accurate claim at some level of abstraction, you can still have other different accurate claims at lower levels of abstraction. So you can just create different causal models, and you could say propose that exactly what you just said, 2 different variables doing 2 different things, and we just try to look for them and figure out where they are. And that, yeah, the process isn't necessarily as simple as you have one causal model, you figure out it's perfect, and then you stop there. It's you've made some sort of structural claim about the type of thing you're looking for. You look for something with that signature, but then you also have to be asking yourself, like, is this signature capturing my own messy idea of what my hypothesis was? And sometimes it won't be. Sometimes it'll be interestingly different in nuanced ways. And if you say, take something like a bubble sort algorithm and think of all the different ways you could write this into a causal model and all the different details you could include or the details you could not include, you'll realize that it's interesting that like something as clean sounding in your head as bubble sort, when you actually articulate the details of that process, kind of like bottoms out in a lot of kind of like different but nearby related causal structures. And in one of my big theory papers, I actually do go through bubble sort and kind of like spell it out as a causal model. So there's an advertisement for gritty people who want to read that. Yeah?
So you started this talk talking about like steering and stuff like that, but like steering, like I think when you do that, like sometimes you fall short because you're like kind of relying on its direction, but it's not necessarily that the model is representing exactly in that direction. Yeah. And I guess even with like casting computation as a causal problem, I'm curious, like, if in your experience, like, what the gap, like, you're not making claims on how the model actually works. You're kind of like, or maybe you are. Like, I guess what I'm trying to get at is like, what do you think is the gap between like how good this actually captures what's going on, and like a gap that's like unexplained? Like, how much of the way are you really getting there with this?
So with this being this very concrete example, not very far of the way, right? This binary carry the 1 variable is a very abstract claim, and you might have questions. Is this this thing, these numbers, are they represented in bits? Are they have, like, what are the underlying feature geometry? What does a 1 look like? What does a 0 look like? Literally in like the vector space level, can we carve it up into pieces? And I would say you can totally do that, and it's interesting to go to more levels of detail and more levels of analysis, and that the sort of like framework allows you to hold off on that or engage with that if you want. So you could say, this seems to be true, but then we go deeper and we find more details of it, and maybe they are, not what we expected, and we find that interesting. I'd say, like, in practice, it really depends. The ultimate, like, full description of a system is probably going to have many different layers of abstraction at which we describe it, and all of those layers might be necessary for us to get a really solid feeling about it. Like, if we're looking at my laptop, we might want to understand assembly code, machine code, Python, like all the way up that hierarchy, and that if we're leaving out parts of the hierarchy, we're kind of leaving out a full, complete description of the system. But that also, if we were trying to understand my laptop and we made statements at one layer of the hierarchy and we could support them really well, I think we'd probably be pretty excited, because it's a pretty hard problem to just engage with a black box system and start getting any kind of traction. So does that work?
One problem that can come up with like the whole like patching or like replacing activations or like adding steering vectors is that you push things out of the like natural distribution of inputs to some layer. I was wondering, to what extent do you, like in causal abstraction, consider that to be like an empirical implementation problem, or is there like, do you consider this potential problem like theoretically, I guess?
That's a great question. So one thing I'll point out, so I think this idea of does an intervention bring your model internals off distribution is a very important question. So if you do a steering vector, you could add that into some place that is basically never active on any actual input to the model. But if you add in the steering vector, the model might still pick up on it, and you might be able to control the model from that location. And so there's something really beautiful, I think, about having our interventions grounded in actual runs of the model. That's interesting. So I'll continue while this loads. So yeah, this idea of that we're going to be performing an intervention, but that intervention is going to be fixing activations to the value that they would have actually taken on some other input is going to keep us on distribution in like a really meaningful way. And some language I find kind of useful to think about it is steering is like, how can I manipulate this object so I can get it to do something? But these interchange interventions or activation patching is saying, the system is doing something interesting. How is the system manipulating itself to do that thing? So we're going to stay very closely on to the distribution of the types of things the system would actually do. And that's going to help us understand the system rather than trying to just control the system. Something that you might have seen in this previous picture is that when we're doing our intervention on the neural network, it kind of looks like we're targeting almost like, if this is like a 4-dimensional vector, it looks like I might be just targeting the first dimension of that vector. So if I just have a list of numbers, which is just a vector inside of a transformer, I'm going to pick out one of those numbers and replace that number with the value it would have taken on another input. But a very popular idea in mechanistic interpretability that I think has given us a lot of successful results is the idea of the linear representation hypothesis, which is that the right unit of analysis isn't going to be these sort of basis-aligned vector units. It's actually going to be sort of an arbitrary direction in vector space. And so you can think of this in the following way. So instead of just taking the vector and doing the intervention, I now want a new unit that I can do interventions on. So what I can do is I can take this vector, I can run some process that I'll just call a featurizer to get me to some new space of variables. So I now have new units I can do intervention on. And then I apply the inverse featurizer to get back to the original vector space. So a very simple way of thinking about this is that F can just be a rotation matrix, and then F inverse can just be the transpose of that rotation matrix. And so if I just run the model with this little featurizing process in the middle, nothing will change on any actual inputs. So there's no loss at all. But what this gives me is now I have these new units I can perform interventions on. And if it's a rotation matrix, what this means is I just basically take the standard axes, and instead of saying I'm going to intervene on these axes, I'm going to instead rotate my my vector space, basically. Yeah, I'm going to rotate my vector space, and I'm going to get a new set of axes that are still equally well equipped to characterize the full space, but intervening on these new axes might be more interpretable. They might better correspond to high-level quantities that I'm trying to localize inside of a network. So if we look at our previous setting, what we can just say is, instead of an interchange intervention, we do a distributed interchange intervention. So we run up to the layer, and then we apply this featurizing process. And then once we have applied the featurizer, we do the intervention. We bring over the feature that occurred for this input and bring it over into this input. And if it's a carry the one feature, then the output will change from 42 to 32. So this is the exact same idea. There's still this sort of structural correspondence of intervention properties bringing up certain behaviors. But instead of intervening on, say, the original variables of the model, we're just doing a manipulation of these variables. And I described it as a rotation, but later on you'll learn about SAEs. And you could equally say that the featurizer is an SAE encoder, and then the inverse featurizer is just an SAE decoder. And so this is going to bring me to an idea that's very important, and I think touches on a question that was asked earlier, which is, how did you find this neuron to do an intervention on? How can we use our hypothesis, our causal model, as a source of supervision for understanding where a certain variable is stored inside of a network? So I'm just going to take this setting again. And so say I just randomly initialized these featurizers, so as a rotation matrix. So I apply a random rotation, and then I perform this intervention. I'm almost certainly going to be wrong. So instead of getting the expected output of 32, maybe it says 98, maybe it just says some garbage number, because basically I'm performing something like a random intervention on this system. But the cool thing is that I actually know what I wanted the model to say. I actually wanted the model to say 32 because my high-level causal model has this structure, and when I do this intervention on it, I get the output 32. And now that output 32 can be used as a source of supervision for training the features of the, that we are intervening on. So crucially, we freeze the weights of the transformer. So the entire transformer is fully frozen, but we learn the featurizer, the rotation matrix. So we're trying to learn a rotation matrix such that when we intervene on the first unit of our new rotated space, it corresponds exactly to the carry the one variable. And so this is a very powerful idea, because now we get to bring the tools of supervised machine learning into this task setting of causal variable localization. So I have a causal variable and a high-level causal model, and I'm using my causal model and how it acts under interventions as a source of supervision for localizing the variable into some piece of the underlying network. Yeah, and then I'll cover the next slide and I'll take questions, because the next slide is a very simple idea. Actually, yeah, we can see how the gradients flow. So if you have supervision up here, gradients will flow down here, and then they flow into the featurizers, not to the underlying model weights, which are, of course, frozen, because we want to analyze the model, not modify it. OK, another core idea here is desiderata-based masking, which is the exact same training objective. But instead of learning the featurizers, we actually just learn masks over the features to select which features to do interventions on. So sparse autoencoders give you a pre-trained set of features that you might not want to update. You might want to keep them fixed. And if that's the case, you don't have to train your features. You can just train masks to select out the features to perform interventions on, and to select out the features with particular interventional properties. So it's a similar idea. And I'll pause on here, because these are some pretty complicated slides that are could be worth thinking about. So does anyone have any questions?
I'm still confused of how you're specifically finding or manipulating that, like, APPPHYS neuron. Like, are you putting featurizers in every hidden layer, and then freezing and then manipulating one at a time? Or I'm still confused of how you're figuring that out.
Yeah, so are we putting featurizers in every layer and manipulating one at a time? So in principle, you can attach these a lot of different places. So in this example, it looks like we're just doing it at one place, basically. Like you might think, I come in and I think, oh, I think this vector might contain a carry the one feature. So then I equip this little featurizer here that's untrained, and then I do this training process to try to find some direction in the vector space I can intervene on that has this property. And so this doesn't solve the problem altogether of trying to find somewhere, because there's lots of different vectors to pick out in a model. And so you could further try to bring in more tools to try to pick out which vector to then do this to. Does that help?
Yeah.
Yes.
We usually do this for like multiple features at a time, because it feels like if you do it only for the first feature, then the other features may be arbitrary or not interpretable in the way you want it to be.
That's another really great question. And that's also kind of a simplification of the slide in some sense. So you can choose any number of features to do this at once. So you might think like it should be 8 directions that correspond to the carry the one variable. You could also do this with multiple variables at the same time. So you might say, I want to learn some features that correspond to the country a city is in, and some features that correspond to the language spoken in that city, and some features corresponding to the numbers of letters in that city name. And that you could try to learn this sort of process to disentangle and figure out separable components that can be intervened on to manipulate individual high-level quantities like facts or numbers.
So because this is localized in one layer, is there any way that this method can like try and discover like cross-layer, like you know, computations that take many layers to complete like induction heads, for example?
So induction heads are interesting because I think you could actually separate them to a couple different variables that you were thinking of, like the copy head variable and then like the something moving over. So when you're thinking about things occurring across multiple layers, something you can do is just train featurizers at each layer and then do all your interventions at once across multiple layers. So this is a pretty flexible idea, I would say, that you can kind of like, this is a very sort of like toy example of how to use this idea. But more broadly, you can kind of just attach these things to a lot of different places and then learn them all separately and do a bunch of interventions at all these different locations. And there's nothing in principle that starts failing if we look about cross-layer or cross-token manipulations. Yeah?
What kind of design decisions do you make for these featurizers? Because there seems to be some trade-off where I don't want to be capacity constrained by my featurizer in terms of what it can encode and decode, but at the same time I want it to be explainable and interpretable.
So that's an excellent question, and there's actually a really great paper that just came out from a group in ETH Zurich that is about what happens if you take this idea of distributed alignment search, but then you start equipping the featurizers with really powerful models, so like 8-layer reversible neural networks. And how do we sort of like manage ourselves in those settings where it seems like those can learn some very gerrymandered and strange ways of cutting up the vector space that seem not exactly possibly to align with what the neural network is actually doing in some sense. And I think it's a very nuanced process. I think once you bring in machine learning tools into this setting, you need to be really worried about overfitting. And that I think connects in directly with your question, where if I'm learning this on, 10 examples of this addition task, it might just sort of like learn some way to get a sufficient manipulation on those 10 examples. And then if I threw in some new 11th example, it would just fail entirely. And so that's why you're just kind of put in the traditional machine learning setting where you need a train, test, split, and you need to like hold out the data that you actually care about, and you need to make sure that the thing that you're learning is a sort of like general purpose, useful explanatory tool, and not some sort of like overly fit, idiosyncratic thing that's giving you pretty fragile results. Yeah.
You could consider a completely alternate strategy, which is for every intermediate step of your algorithm, different nodes of your causal graph. For some ensemble of math problems, try to linearly decode the intermediate states of your causal graph from every single layer and position.
Yeah.
And see which layers and positions encode that variable to localize it. So you're just doing linear decoding.
So if you do that, you basically just get a very sort of like, if you make heat maps of doing linear probes versus doing this, the linear probe heat map kind of lights up everywhere, like even to the very final layer of the network, which is a very good thing to think about because it's like, if you're at some token and you're at the very last layer of the residual stream, that literally has no causal impact on anything, but it's still a very rich representation. Like the model wasn't told to destroy pieces of information that are present in that vector. And so generally, like probing can sort of like show you where relevant correlational information exists, but it's going to very sort of like fail at trying to show you what the actual path of that information as it's like truly being used by the network.
So here what you're doing is you're taking the carry bit and trying to predict what the next variable should do using that carry.
Yeah. It's kind of like a causal version of probing. So it's not just probe out the information. It's like learn these directions such that when we manipulate them, they correspond to downstream effects that are in concordance with this carry the one variable.
Okay, so if you did this featurization of every position and every layer and looked at the heat map of performance for, say, the carry operations prediction on the next part of the algorithm, what would that heat map look like? Is it very localized?
Very localized. Very localized. Like last token, like layers, like mid to late layers, but a cluster of like 4 or 5 layers. So that's the beautiful thing, that when it starts working, it really starts working, where you see these like highly contrasting heat maps that are like, actually, this piece of information is really just present here, in a similar way to like in the causal mediation setting, where it's like, yeah, really it seems like this chunk of MLPs are just the MLPs doing this, extracting out Seattle from the Space Needle.
Does intervention on one unit will change the behaviors of the other units? In other words, like, are they sharing the same set of rules for the condition or not?
So because this is basically like an invertible process, like it's a rotation matrix, that means all our directions are orthogonal, so there's no interference between these units. So these little triangles here are all separable, so you can intervene on one and intervene on the other, and that operation commutes, and they don't really interfere with each other. It's not so much the case if you have something that's more lossy, like a sparse autoencoder, that will like unpack into many different directions that have interference with each other and then come back. But generally, if you just add back in the error term to a lossy process, you can still talk about it like it's an actual bijective process, because it's just, I don't know, that's just basically a little trick. And that is the way that SAE manipulations do it. Like they will throw back in the error term at the end just to make it, well, not because they want it to be principled and nice, just because that's what makes it work, basically. Yeah.
Are you always guaranteed to find a solution? Like, in this case, it's simple because, you're set to carry the one, but is it something about cases where you break that?
That's a great question, and absolutely not. And I think that's one of the things that tells us that we're doing actual science here, is that you regularly fail. You regularly propose some intuitive quantity in the middle of a network that you're like, yeah, I would do this. And then you look for it, and it just entirely isn't there. And so I would say, yeah, definitely, yeah, basically just no. And, in the worst case scenario, when people talk about these things being statistical stochastic parrots or whatever, it's just a giant lookup table with no internal structure whatsoever. I don't think anyone really believes that nowadays, but that's definitely the type of ideas that were being thrown around in like the early 2000s. And also maybe the models were closer to being that in the early 2000s as well. So there's that. But yeah.
I'm wondering the dimension of the visualizer or the rotation matrix. Is there an optimal dimension that's under 2, or is a scaling?
So in principle, like the rotation matrix, is like a full rank thing because it's a rotation matrix. But if you're only trying to learn like 8 features, you don't have to learn most of the matrix. You only learn like 8 directions there. Is there an optimal number? Like, is 2 directions better, or 1, or 8? Completely depends on the causal variable you're trying to localize. For something that's very simple, like sometimes 1 direction completely suffices. But for something that might look more like an actual token embedding, that's kind of this chunkier thing inside the model, it might need like 64 dimensions to actually capture the whole thing. Yeah. And that's something interesting there, where it's like we're not getting a super detailed look at the feature geometry of those 64 dimensions. We're instead just getting we're getting just this claim about how they act sort of in aggregate together when we do interventions on them. I'll have some pointers to literature here. So, and there's also a lot of papers that explicitly have used causal abstraction as the framework for analyzing models, which is exciting. And some of them I'm not authors on, which is even more exciting for me. So that means there are other humans in the world who think about things this way. Also, there's like a developing theory of causal abstraction. A pretty exciting thing is that this is a pretty young field theoretically as well. Like 2017 is really the sort of seminal paper that brought out these ideas about looking for structural correspondences between two causal models. And it's really been, less than 10 years that we've even really been like making progress on these ideas. But a bunch of Europeans who love causality are increasingly into these ideas. So that's also pretty fun. And then also desiderata-based masking, worth knowing about that citation. Cool, well then I'm gonna walk through, and this part is gonna get very hairy very quickly, so I apologize, but I just wanna give you a flavor of like what the kind of like human-inspired aspect of doing this type of causal analysis is as we move into a more complicated setting than looking for a single binary variable stored within a network. So in this paper, we look for, or we discover what is basically this pattern of a lookback. And it's a very intuitive and simple pattern. It's just if a neural network wants to keep track of a piece of information and then go retrieve that piece of information, what it can do is it can put a little marker on that information and then create a copy of that marker later on that you can then use to sort of dereference and look back and grab whatever was relevant in your context. So to ground us in a very specific example, the example down here is a little story where Bob fills a bottle with beer, Carla fills a cup with coffee, and the question is, what does Carla believe the cup contains? So this is exactly what this templatic data set is. It really is just this exact template, except these highlighted color words of Bob, bottle, beer are being replaced with different characters and different containers and different substances. And we developed this sort of end-to-end mechanistic account of how the model is solving this task. And it does so in a really weird and complicated way. So I'm just going to walk through at a very high level what this kind of looks like, and then I'll zoom in to some of the particular claims and the experiments that we did that we think justify them. So what does the model first do when it sees Bob, bottle, and beer, and Carla, cup, and coffee? It first assigns them positional markers. So now Bob is no longer Bob. Bob is actually character 1. Bottle is object 1. Beer is state 1. And same thing goes for character 2, object 2, and state 2 being Carla, cup, and coffee. So these are now positional markers that the model is going to reason about instead of the actual tokens themselves. So how does the model formulate a query, formulate the question, what does Carla believe the cup contains? Well, the model sees, oh, Carla and cup. I'm going to look back and grab the positional markers for cup and the positional marker for Carla and bring them forward into my residual stream so I can form my query like Carla, cup, question mark. Now that I have Carla and cup's positional information, I can use that to look back and grab the positional marker for coffee, which is the answer to my question. But this is still the positional marker for coffee. It's not the actual token itself. Then it does another look back mechanism. It uses this positional piece of information to look back and grab the token itself, coffee, to answer this question. And so there's sort of 3 stages to this process: assigning of positional markers, formulating a query by retrieving the positional markers about the nouns in your question, and then grabbing the actual token itself, or grabbing the marker to the correct answer and then grabbing the actual correct answer itself. And so I'm just going to zoom in on one very specific step of this process and just talk through the experiment that we did and why we think it justifies the sort of picture I just presented. So this picture here is saying that I have a positional marker for the word coffee that I use to go retrieve the actual token coffee. So I want you to consider this following counterfactual. So all that we've done here is that we've swapped the position of Bob and Carla and cup and bottle. So Carla and cup appear first here, and they appear second here. And then we've replaced the liquids, tea and water, with the liquids, beer and coffee, or vice versa. So we have two different stories, and what's happened is we've swapped the order of the characters and the containers, and we've sampled new substances. So why did we construct this counterfactual in this way? Well, the output for this story is tea. The output for this story is coffee. So if I paste in the output for this first story over the output for this second story, the output should change from coffee to tea. That's just a very obvious and basic statement. This network provides two different outputs on two different inputs. And if I paste over, say, the final layer of the residual stream for the last token, I am logically guaranteed to change the prediction from coffee to tea. But what if I instead paste in the positional marker for the word tea over the positional marker for the word coffee? So what happens in this original story here with coffee is it has a marker that says, grab me the thing in position 2, which is coffee. Coffee is in position 2. It's after beer. But if I paste in over that, get me the thing in position 2 variable, and I paste in the t position variable, where t occurs in the first position in this story, I've now manipulated my pointer from pointing at the thing in position 2, so it now points at the thing in position 1. And the thing in position 1 in this story is beer. And so if I see the output beer, this is a piece of evidence that I've discovered a positional marker separate from the actual final output variable. And indeed, when we do these interventions on the residual stream of the last token in these examples, at layer 30, we actually see the positional signature all the way up to layer 50. So through these layers, if we do this intervention, we see the output go from coffee, the thing in position 2, to beer, the thing in position 1. But if we continue to do the interventions at these layers, there's a transition to the model outputting tea instead, which is just the output from the counterfactual story. And so this counterfactual is very nicely set up such that the final answer, manipulating that information, is going to give us a distinct output from manipulating what is essentially like a positional pointer to the correct answer. And so, yeah, and so this is the type of analysis that you have to do if you want to sort of construct the right pairs of examples that are going to be able to sharply test the hypotheses that you're proposing about how models actually process their inputs and solve the tasks that we're giving them. I'll pause here in case people have questions, because I know this gets messy, and it's pretty fast.
Yeah.
In this graph, what is this business of subspace dimension being less than 20.3?
Yeah, so the solid lines are if we're just patching in the full vectors. But then we also do this masking thing where we learn. It's actually SVD decomposition. So we take vectors, we collect them across all of these prompts. We do SVD to decompose that into a new, like basically just rotation matrix or whatever. And then we learn masks over the SVD components and then intervene on those. And so this residual stream has like, I don't know, like 1,000 units or something. I don't remember the exact number. But we actually only need a 20-dimensional subspace to do this manipulation. Yeah, which is actually a very tiny subspace. So this positional information is stored right there. And it's interesting, too, because the subspace sizes shift. So for this positional piece of information, it's like generally less than 20. But for the final token, it's like generally less than 33. And in general, tokens are just kind of chunkier inside networks.
So how close do you get to the full residual kind of graph if you vary the subspace dimension? Does it follow sharply, or does it follow sort of smoothly?
I don't think we have results on that, but that's a really good question. And I think in general, I think those are pretty good plots to try to produce that, like, as you increasingly get smaller, almost like what's the topography of the thing? Like, are there really crucial tiny bits? I think that'd be pretty interesting experiments to do. Yeah?
So in this kind of setting, you can be pretty sure that you've kind of designed a counterfactual that is like appropriately controlling for all of the confounding variables. Is that something that you think can scale in general to like more complex experiments you'd like to run?
Wow. That's like such an excellent question. So it was actually doing this project that made me feel very strongly about a couple things. One is that I needed a code base that actually expressed the causal models as Python objects themselves for analyzing these counterfactuals and figuring out whether I'm doing the proper kind of hypothesis testing. Because as you can see in like the previous image I had, we're dealing with something like 9 variables now or something like that. And it's just kind of like messy, kind of like trying to figure out how can I localize exactly this positional marker separate from all these other possibilities. And what's more, that's just the possibilities in the causal model I proposed. And there's always other causal models that might just do things completely separately. But that being said, I do think there are sort of like, I do think there are interesting, like rich theoretical things you can say about how to design these counterfactual data sets and what the sort of like workflow for doing this like causal analysis is when you're trying to distinguish between particular hypotheses. And from my perspective, broadly, like this is actually what I'm like most working on right now, is developing like the sort of like theoretical understanding of like what that workflow is, how to design these counterfactuals to distinguish between distinct hypotheses, and then trying to scale that process up using like agents, basically. And it's a very exciting perspective for me on how we can scale interpretability, because I love bespoke analysis. I love looking at a very specific task in a very specific model and just really trying to understand end-to-end what is happening. And I think there's this sort of like alternative route to scaling interpretability where we just embrace that process and just try to do all the work we can to flesh out what it looks like and try to plug that into basically like science assistant agents or something like that.
Yeah. Is there anything unique about the location in the layers, like where you're seeing these positional embeddings, or like you said with other examples, does it depend on the type of sentence you provide? Like,
that's another really great question. So, you know, in this, I think this paper is like a really great example of us focusing on a small data set and just like going really hard on it and trying to figure out just like the whole process end to end. But that, honestly, there's like not enough papers like this yet. Like if we could like have a view of like 100 papers like this where like they've done a bunch of different tasks, I think we could start noticing cool patterns. Like, is this layer where positional stuff just seems to happen? Like maybe the model is just reasoning about positional things here, and then here is just the hard cutoff where it's like, all right, time to move on from positional markers and actually grab the tokens that I need for things. And I think that'd be a pretty interesting question. And I think generally looking for these sorts of like computational or algorithmic motifs in models is a pretty exciting research direction. Yeah.
How important is the character or object encoding relative to each other? Because you could choose one or the other and still get the right answer. And so comparatively, how much do you get?
That's a really good question. We did not do, I actually do think we did some experiments about this. They might have made it into the appendix of this paper. It's complicated. I think the kind of way you want to make the statement is something like, if I just replace the character or the object positional information, and that's like part of my query, what is the resulting decrease in logit strength for each of the answers? I think is probably the reasonable way to think about that. My guess would be once you put in conflicting information that it kind of like is not sure what to do. It kind of like decreases confidence in the right answer. Whether one of them is going to be more important, I'm not really sure about that. Yeah.
So it seems to me then that like the positional embeddings or IDs that you have here seem almost like necessary for this circuit to take place. Did you like try ablating that? What happens in that? Like what does it output? And can you train a model from scratch without them to still develop this kind of behavior?
That's a really good question. So I'm not sure about the training from scratch thing, but we do variations of the absolute token indices that things appear at, and that helps us distinguish from positional embedding itself. I think these positional pieces of information are a lot more contextual and relativized than like an absolute index within a sequence of tokens, which makes sense. And I would also, my guess would be training from scratch, models just have to figure this out. That like sort of like contextually relevant pieces of information are just never going to be at like absolute indices that you can always just go to and understand. And you need to understand like what's the third character referenced in the last paragraph is a relevant query that models need to handle.
Yeah.
Does this structure of like relative token position emerge in model train on less structural data sets as well? like less complex data sets?
These are just pre-trained models. This model is not fine-tuned on this data set at all. So this is just purely a pre-trained model, like it's Llama, and no fine-tuning whatsoever. So definitely. Mm-hmm.
So this kind of reminds me of, there was like a meme about like a prompt you could write to ChatGPT about how many R's are in strawberry.
Yeah.
So the model would fail, but like I guess my question is like, you could write it the word, but it would still fail. But like, could you view like, I'm not sure if this fits in with this type of research. Like, if you were to, let's say, write the word strawberry but do a misspelling of it, does it refer to your actual prompt, or does it refer to its like training of the word strawberry?
So I think that's just all going to come down to tokenization. Like, if you misspell strawberry enough, what are the actual tokens that word is split into? Because I imagine at some point it's split into a token that's just like a bunch, and that's going to kind of crucially come into play. And I feel like that strawberry meme is all about the fact that models have token representations, and those tokens can't, unless they train them to, unless the model learns it, doesn't necessarily contain character level information.
And notice that the graph is like a little bit spiky at the
Yeah.
top. I was wondering if you just attribute that to noise, or if you like, is this something like, oh, this information, something happens at layer 30, then this information kind of sits there, maybe there's a little noise, and then something happens at layer like 55 or something.
Yeah, that's a great question. First, I'll say this is a beautiful graph, considering like the types of graphs you'll often see. Like, this is like incredibly clean, but that like generally things don't happen all at once in models. Like, they have a whole bunch of layers, and something you'll very typically see is like, oh, I think like this token starts at this place in the input, it goes up, and then the signal for that token goes down gradually across layers, and then you see it pop up in this other column of the residual stream gradually across layers. And there, it's just multiple attention heads are like moving this information bit by bit across it. But an important thing to consider there is that's not necessarily what's happening. Like, another totally reasonable thing to think is that like for some inputs, it's entirely moved. And then for other inputs, it entirely stays in place. But because our graphs or our heat maps are on aggregate across many pairs of examples, it kind of confounds those two possibilities. And you need to do sort of like more detailed analysis to tease them apart.
Just to that point, the story that you had earlier, like very early part of the lecture, where you would intervene with noise and then restore something at a particular layer, that would be an example of a way that you would be able to tell whether or not the thing had been moved and there was no more moving of the information anymore after that point, right? Because if it was just moved and there was nothing else doing it, then it would only be one layer that would have that restoration quality, right?
So that's true, but also those graphs were 10-layer restored at once. And so when you actually look at the other graphs in the paper, those were like the headline graphs to show this like nice chunky, whoa, heat map looks discrete type thing. And then the other graphs in the paper are much more gradual because they're doing individual restorations. And yeah, often, especially with MLPs or attention heads, it's like almost never going to be one layer just boom, does this discrete operation. It's going to be distributed across multiple layers and multiple modules working in tandem. I'll end on a different paper, and this is just food for thought that'll be over in 1 minute. It's just, what happens if we go from just two things to lists of things, like long lists of things? Does this exact same positional mechanism occur? And the answer is actually no. So in the setting where you just have these two things, like Bob, beer, Carla, coffee, the positional mechanism explains everything perfectly. But actually, if you get increasingly long lists, the positional mechanism degrades in the middle of those lists, and it actually relies on a direct lexical lookup for those positions. So instead of saying like, Pete loves jam, and that's in position 3, so when I want to grab jam, I use a position 3 marker. Instead, I just directly use the token Pete to look up and grab the token jam. And so this is kind of like the positional results. So like up here is like perfect, and then down here in the middle, it gets much, much lower performance. And then at the end, it gets really high again. And so this is just like a nice little U-shaped thing showing that when we were in this previous paper, when we were looking at just lists of two things, It's super sharp analysis, like really clean, like kind of exactly what's happening. But if you even just like look in very slightly more complex settings, the mechanisms used actually are kind of like a mixture of mechanisms where there are multiple things at play, and depending on the type of input and the type of question I'm asking, will modulate what the actual mechanisms the language model uses to answer the question. And so that's just to say that, I think it's nice to look at very narrow settings and get a really crisp, clean analysis. But I also think it's really important to increasingly kind of embrace the mess and model these objects as directly as sort of having these like layered algorithms or heuristics that they learn throughout a training process, and that it's not going to necessarily come out to be just this crisp single algorithm that just solves the process end to end. And yeah, since we're at time, I'll leave it there. If you have more questions right now, I'm happy to take them. But yeah, thanks so much, you guys.